right, let's go and review some things we've talked about the last couple of days. Yesterday, we worked with plane mirrors quite a bit and worked with really the two laws of reflection. The first law of reflection being, Kendall, that?
Angle of incidence equals the angle of reflection.
Good, and we saw that demonstrated multiple times as we could see those beams traveling. But also, the second law of reflection, Audrey. We had this challenge as we were trying to get the light beam down the stairwell. And we had to make sure we angled it properly, not just angled it, but angled it, right? Because the, Michael? Everything, the incident ray, reflected ray, and the normal all have to lie in the same plane as well. So not only will the angles be equal with respect to the normal, but they have to lie in the same plane. So the way in which we tilted the mirror very much affected how we directed the laser beam through the hallways and down the stairs and stuff like that. The study of light, Audrey, is called optics. And specifically, we're just treating light as the traveling of individual rays that run parallel to each other from a light source. This study class is called geometric optics. And the use of lasers is helpful in geometric optics because you can see the beam or the ray individually. When light strikes the surface, light comes back off the surface. Now, does all the light reflect off the surface? No. A percentage of light does. And with every subsequent reflection, we noticed a couple things. First of all, since our mirrors are cheap plastic mirrors, they were not optically flat. Okay, and so the beam would get distorted every time it would reflect. But also you lose a little, wouldn't you? Right? Some of the light gets absorbed by the mirror, and so the laser beam would get not only more blurred, but also weaker the more reflections it took, until by the end we were just trying to get any semblance of green into the nursery. Did we ever get it in, or no? We ran out of time. We were close. We were close. We got it down to the bottom of the stairs. We just couldn't get it that final bounce into the nursery, and that was, whatever. That's a hard one to get. But this percentage of reflected light, or the ratio of reflected light to all incident light, Kendall, is called reflectance. We said there's two types of reflection. Whether or not a clear image is produced. What are these two types of reflection, Michael? For instance, if I look into my white paper, there's plenty of reflection, but I don't get a clear image. If I look into a mirror, I do get a clear image.
Specular and diffuse.
Specular and diffuse. Which one's which, Audrey?
The specular gives you a clear image and the diffuse does not.
All right, and why do we get specular reflection and diffuse reflection, Kendall? What causes this difference in whether or not an image is produced? Let's see if I can see Kendall here. Where'd you go, Kendall? That's Miss Morse's desk. Kendall. Why might I, if I could ever find you, why might I be able to see you in this? Or at least I see you in this part of it, but not this part of it. It's a lot easier with my phone yesterday. Why could I see you in this part, but there's no way I'd see you in this part? What?
It's clear.
No. Audrey?
The parallel rays still stay parallel.
Off of a
smooth surface.
Smooth surface, right? Smooth surface produces that specular reflection because parallel rays stay parallel. Whereas on the uneven surface, those parallel rays are reflected all over the place, reflected all different directions, right? By the unevenness, so that's producing the diffuse reflection. We talked about, we used these yesterday, these flat mirrors. Class, what's the name for a flat mirror? A plane mirror. We did a little math with the plane mirror at the beginning of the hour. I said, basically, you just need to remember that because the angle of incidence equals the angle of reflection, with a plane mirror, just cut everything in half, right? Because the angles are the same, the distances will be halves of each other. So basically, if you wanted a mirror to see your entire body, you would need one that is half your height. So Michael, you need a mirror that's at least, 3 feet, maybe 3 feet, a couple inches. And then Kendall would need something that's at least a foot, a couple feet, 2.5 feet-ish tall. And so again, the size of full-length mirror you need. Now again, the biggest humans known on Earth today are some of our giants in the NBA, 7'4", 7'6". If you have a 4-foot mirror, is that going to take care of that guy? Yeah, because a 4-foot mirror could accommodate a person up to how tall? 8 feet tall. Now, you just have to hang the mirror a little higher for the taller people. But most full-length mirrors are between 4 and 5 feet tall because that would accommodate anyone. Anyway, with a plane mirror, we said there's 5 characteristics of a plane mirror image. One of those things is that when you look in the mirror, you're standing up, you're standing up. If you were, for some reason, to be standing on your head, you look in the mirror, you're standing on your head. You see yourself oriented as you are. We would say, then, what was that term? For an image that is, well, perceived as it is. The term is upright. Class, what's that word?
Upright.
Upright refers to an image not being flipped upside down like the inside of a spoon. There's a chair there. All right, an upright image. Also, when you look in the mirror, we said that not all the light reflects off. So because some of the light's absorbed by the mirror, the image that you see reflected is slightly... Well, if the mirror is distorted, like the one inside my cabinet we noticed the other day, then you'll be slightly distorted too, but or the image would be rather. Slightly darker. Remember, the image is going to be slightly darker. That's not very important, but it's a thought, right? There's a reason why the concept of infinite images is rather hard to manage, unless you get really highly polished silver or something like that. Wouldn't lose a whole lot of reflectance there. Another thing is when you look in the mirror, you see the size you are. If I put this water bottle in front of a mirror, whatever size it is, that's the size it appears in the mirror. Now, as you get further away, right, you get that distance, like, you know, I see Audrey, I'm like, hey, she looks this big. Well, she's not that big. That's because of the distance I'm at and the placement of my hand, right? But if you see the size you are, we would say then that an image is unmagnified. What's that word, class? And these are all terms we're going to be using here in a little bit for other mirrors as well, so you want to be familiar with them. Unmagnified. Next, when we look at a mirror, again, I look in the mirror, if put the water bottle in front of a mirror, where is the water bottle's image? Where does the reflection appear to be? Behind the mirror. And as I move it closer, it moves closer as well, but it always is behind the mirror. Well, do light rays really reflect through the mirror? No, they reflect off the mirror. But it seems like they're reflecting into and behind the mirror. So we'd say that the image formed by a plane mirror is, class? Virtual. What's that word, class? Virtual. The last thing that we notice is, and I kind of alluded to it a second ago, but remember we said if you were to raise your right hand, then if you were looking at the reflection, it would raise its left hand, right? And so we said that the image produced by a plane mirror is also reversed. Now, do you remember which axis the reversal takes place on? I showed this a couple days ago. If I point this way, it points that way. If I point this way, it points that way. If I point this way, it points that way. The z-axis. Remember, not the x or the y, but the z-axis is where the reversal takes place. How did I say you could correct this reversal? You could get the image to actually do as you're doing. 2 mirrors, right? Or really an even number of mirrors, but 2 is the easiest way to do it, right? 2 mirrors will unreverse an image. All right, questions on plane mirrors. We talked a lot about them, played around with them yesterday. We understand plane mirrors. Let's talk about what you read about in your homework reading 2 nights ago, and that is spherical mirrors. Next term in your notes, next section in your notes, I should say. Spherical mirrors. I'm not going to insult you with a definition. Spherical kind of says it all, right? Ickle, like pertaining to. Sphere, mirrors that pertain to spheres. Basically, there's a big ball, a sphere, and it's a mirror. Or at least a mirror came from the sphere, right? 2 types of spherical mirrors, and I referenced this when I was going over the homework answers the other day. But if you have a great big ball of mirror, and the ball is reflective all over the outside of the ball. You've actually probably seen balls like this that are shiny and reflective. Well, if I were to somehow cut the ball and just take a piece of that spherical mirror, the mirror's surface kind of bulges outward, right? Like if you eat too much. kind of bulge outward, right? And maybe after a big meal, or maybe several big meals around holiday time, and Audrey's like, I don't know what you're talking about, Mr. Dusky. I didn't either when I was your age, okay? And I was bulging outward, and maybe it bothers me or vexes me a little that I'm bulging. Like, I really should lose weight. Diet? No. Exercise? No, I'm not that vexed. But it does maybe vex a little when you bulge a little. Well, a mirror that bulges outward, or that has the reflecting surface on the outside, is called class A, convex mirror. Here's what you need to know. Not that it's bulgy, though practically speaking we could say that, but the reflecting surface is on the outside of the sphere. Reflecting surface is on the outside of the sphere. Practically speaking, think of bulge and think of being vexed by bulge, okay? But practically, definition, if the reflecting surface is on the outside of the sphere, we have a convex mirror. And we said also, if you have a ball of mirror, and maybe on the outside it looks like any other ball, but when you cut it open, you're like, whoa, it's reflective inside. Right? For instance, the spoon, right? Turn it one way, it bulges at you. Turn another way, it's like a cave going inward. Not much of a cave, admittedly, but that's kind of how we remember that one as well. And I think these are terms you've learned in years past, right? So this is perhaps even how you learned them. But a concave mirror, it caves in away from you, like you could walk into a cave, though it's not much of one, admittedly. Here, the key is to remember that the reflecting surface is on the inside of the sphere. The reflecting surface is on the inside of the sphere. So we have these two types of mirrors. Several parts of a spherical mirror that you need to know. The first is called the vertex. The vertex. We're going to label it on diagrams and pictures with the letter V, because it starts with a V. Vertex. The vertex is the center of the mirror's surface. The vertex is the center of the mirror's surface. Now, whether it's convex or concave, it really doesn't matter, right? You could set the mirror down so that the cup is upward, correct? Now, if it's convex, then the mirror will be aimed down at the tabletop. If it's concave, the mirror will be facing up at you. Either way, the center of the surface, the point on which the bowl, if you will, would sit, is the vertex. It's the center of the mirror's surface. Now, we can't really draw in 3 dimensions. Your textbook has a little illustration, if you will, on page 282, kind of a 3D look at what a convex or concave mirror could look like. For our purposes, we're going to draw it like that. We're going to draw it as a cutaway, if you will. So we can't draw it in 3 dimensions, so we'll just draw a cutaway arc to represent the mirror. If the reflecting side is over here, it's convex. If the reflecting side is in here, it's concave. But the very center of the surface is the vertex. Does that make sense? The next term we need to know is the term center of curvature. The center of curvature. Represent this with the letter C. The center of curvature is the center of the sphere. The center of curvature is the center of the sphere, from whence the mirror cometh, forsooth. The center of the sphere. Imagine, if you will, again, we're looking at this in 2 dimensions, but imagine, that's a terrible circle. Pretend that's a perfect circle, which would be the cross-section of a sphere. All right, roughly speaking, because it's a very rough drawing, we'll just say that this is the center of the sphere. If so, we call it the center of curvature. Make sense? So the vertex is the center of the mirror itself, or the center of the surface. The center of curvature, class, is the center of the sphere. Do we understand the difference between them? All right, now if we were to draw a line through the center of curvature and through the vertex, this line through C and V is called the principal axis. Principal meaning the main one. The principal axis is simply a line through C and V. Might be a good way to define it. Now that we've specified what C and V stand for, we can use those abbreviations and say that the principal axis is the line through C and V. Now, question. How many lines could I draw through C that actually go to the mirror? An infinite number, right? I could draw an infinite number of lines. Those would be considered secondary axes. We don't need to know that, but you could draw a whole lot of axes. The principal axis is called the principal axis. It's the main one. It's the one that goes through C and through the vertex. Make sense? There's a lot of vertices, if you will, that we could draw. Now, the distance from C really to any point on the mirror, but specifically from C to V, that distance is called the radius of curvature. And it makes sense why. It's the distance from the center to any point on the surface. So this, the radius of curvature is the distance from C to V. It's that length, CV. It would also be the length from C to any other point on the mirror, but since we've already defined point V, let's be lazy and just say it's the distance from C to V. The center of curvature, or the radius of curvature, rather. Now, if we were to draw a radius of curvature to the top of the mirror, the top edge, and draw a radius of curvature to the bottom edge, we would form an angle here at the center of the sphere. We call it a central angle, but specifically this angle shows how wide the mirror opens. You realize I could make a spherical mirror that looks like that. That's still spherical. Now, it kind of looks like a straight line, but it's technically a spherical mirror. It still came from the sphere. It's just that the mirror part was smaller. Well, you notice I'm going to get a smaller angle as well then, correct? We refer to this as this kind of describes how big the mirror opens, if you will. Does that make sense? How wide the mirror opens. And the term for an opening is aperture. Aperture. So we refer to this as the angular aperture. Know that term. Is it aperture or aperture? I think it's just aperture. Yeah, no A. All right, the aperture. I'm terrible at spelling. The aperture is the size of the mirror, how wide the mirror opens. Two types. The angular, and the angular aperture refers to the angle of the two radii. There's another way we could measure, though, and I could just say, from the top of the mirror to the bottom of the mirror, how tall is it? Or, if we went back to the original mirror that we had a second ago, right? It was a mirror that looked like this, remember? Well, I could measure, okay, from the top of the mirror to the bottom of the mirror, how big is that? It's kind of like the diameter of the mirror, if you will. Right, that's a little easier to see. That's called the linear aperture. So when we think of the linear aperture, we're literally thinking about what's the diameter of the mirror, how big is the mirror, like how a normal person would see it. But the angular aperture actually is more important. For instance, let's suppose I had a, again, my drawing is poor, but we'll roll with it anyway. Let's say we have a circle, pretend that's a circle. We have a circle this big, and we've got a circle this big. And if I were to slice the mirror right here, and if I were to slice the mirror right here, roughly, this is about, no, it's not the same linear aperture, not at all. Okay. Okay, now the linear aperture is roughly the same. Do you see that? But for this one, you see the size of angle? It's a decent size acute angle, maybe around 50 degrees. For this one, if you look at the angular aperture, same linear aperture, much smaller angle. Does that make sense? So the larger the sphere from whence the mirror cometh, the smaller the angular aperture for the same linear aperture. And again, we're going to see why here a little bit later on in this chapter, why a small angular aperture can be a little bit better for our purposes. All right. Questions on these terms so far? Now, we know this, that with our mirror, and to tell you what, let me ignore that drawing, we'll start over here. Let's just say we've got this curved surface. Let's say roughly right about here would be the center of curvature, roughly right about here would be the vertex. So here would be my principal axis right through my letter V I just wrote. Okay, so this would be roughly my principal axis. We know this, that when light rays strike a surface and they reflect, which is the point of a mirror, the angle of incidence equals the angle of reflection. But on a spherical mirror, you're dealing with a curved surface. And so we said these angles of incidence and reflection are measured from the normal, but how do we determine the normal on a curved surface, anyone?
The tangent.
It's perpendicular to the tangent. So imagine for a moment, I've got this light beam, this light ray that comes in and it hits right here. Well, at this point, this would roughly be the tangent. This would be the normal. Well, let's think back. Michael, you're in geometry right now. What is always perpendicular to a tangent? The radius, technically. Okay, so if I really wanted to, I should draw this line right here. That would be the perpendicular, go right back here. And so this angle of incidence has to equal the angle of reflection. And so it's going to come roughly to this point here, right? Well, I could do that again with maybe a blue ray. See what I did there? Anyway, we can do that with a blue ray. Okay, it strikes here again. Here's the normal to this tangent, if you will. There's the angle of incidence, there's the angle of reflection. The light ray is going to come through like that. We could do this over and over again, but what's going to be unique based on the way it's curved is because the angle of incidence equals the angle of reflection, and because we're coming back to these radii as the normals, all these light rays, theoretically, should converge roughly at the same point. The light rays will all focus, if you will, at a particular point that we call the focal point. So that's the next term to know, the focal point. Now I say roughly. It's not going to be perfect if the angular aperture is too great. A small angular aperture, this will be more true. But with a small angular aperture, the light rays will converge either at or roughly at a particular point called the focal point. Now, that's if the light rays are some infinite distance away and the mirror rather, is aimed at the light source. But we know this from just playing with the plane mirrors yesterday. What if I tilt the mirror? What happens to the reflected beam? It tilts with it. So imagine if I take this mirror now and I tilt it up a little bit. What's that going to do to these rays? It's going to push them up. So instead of converging here, they might converge here, or here, or here. Or if I tilt it down, they might converge here or here, depending on how much I tilt it. The light rays will all converge somewhere along this plane called the focal plane. So the focal point is where light rays should theoretically converge, or they would converge along the focal plane. I'm going to call this point on the principal axis F for the focal point. So let's note that. We'll use the capital letter F to indicate the focal point. And again, that's assuming the mirror is aimed perfectly at the light source. Light rays would converge at that focal point, approximately, if it's tilted along the focal plane. What's interesting is, if you were to measure from the focal point or focal plane to this vertex, that distance will be the same as the distance from the center to the focal point. We call this length right here from the focus to the vertex the focal length. We represent it with a lowercase f. Focal length. It's the distance from F to V, but it's represented with the lowercase letter f. Like frequency, but it's not frequency. So the lowercase letter f is used to indicate the focal length. The radius of curvature, by the way, since it's radius, it's going to be represented with the letter r, going back to radius of curvature. It's the distance from C to V, but it's represented by the letter r. Since the focal length is the same as the distance from center to focus, then the center to vertex will be twice as big as the focal length. That is, that the radius of curvature will be double the focal length. Well, normally the radius of curvature is something that's known already. Usually we think about it from the other direction, and that is that the focal length then is half the radius of curvature. And that's the first equation for you to know in this chapter. That the focal length of a spherical mirror is half the radius of curvature. A lot of terms, a lot of explanation for the design and how things are going to work with the spherical mirror. Before we get into more functional stuff, questions on this? All right. Now, if you look in your textbook with me there at page 282, you see all of these terms. You see all these different points. We kind of see some diagrams with cool light rays that look like, you know, something out of Star Wars. And so we see all that cool stuff. Again, if the light source is that infinite distance away. Now, does infinite really have to be infinite? No, not really. For instance, if somebody had a flashlight at the other end of the PE field over there, and I had a, standard sized spherical mirror, maybe, so big, that might as well be infinitely far away. It's really far, okay? Versus if it were in the room still, I wouldn't consider that an infinite distance. But if you're that far away, it's practically infinite. You would still get that dot of light roughly at the focus or along the focal plane. Certainly the sun's distance from us could be considered infinite, right? It's not infinite, but compared to the radius of curvature, it's so far away, we can practically say infinite. So infinite doesn't have to necessarily be infinite for this to achieve. However, as the light source moves closer, we would notice that the image would no longer be formed at the focal point, but the dot of light as the object, as the light source, maybe the flashlight moves closer, the reflected beam would start to move further away, where the light reflects off. We can track this by using something called a ray diagram. You see that term on page 283. A ray diagram is simply a picture that uses three principal rays. A ray diagram is simply a picture or a sketch, if you will. Maybe sketch is a better word for it. A sketch that uses three principal rays to determine the size and location of an image. A ray diagram is a sketch that uses three principal rays to determine the location and size of an image. Three principal rays to determine the size and location of an image. Now, if the object in question placed before a mirror is literally just a point of light, it calls it a point source. If it's just a point of light, then obviously you will get a point of light as your image, right? The question is, where will this point of light be formed? Well, notice they have three rays coming off of that L light source. They've got a blue ray that goes parallel to that principal axis. Do you see it? And we already said that if light rays come in parallel, they're going to reflect off through that focal point. They've got another ray, the red ray, that's the dark side of the force, that goes through the focal point, hits the mirror, and it's going to reflect parallel to the principal axis. The final ray goes through the center of curvature, travels along the radius of curvature, hits the mirror, and bounces back. That's Yoda. All right? So we see where those three rays all converge. At that point of convergence, that would be where the image would be formed, where that little dot of light image would result. Does that make sense? And the problem is you won't be able to see that dot of light. Unless you were to somehow maybe take a piece of paper or even a little 3x5 card and kind of play around in front of the mirror. The light source is up here, so you kind of come down below the light source and wait until you get the spot where it focuses nice and brightly. Challenging to do, but doable if you have the right apparatus. Now, what if we had something that wasn't just a dot of light? What if we had an illuminated object, maybe a cell phone, for instance, with a picture on it? It's still producing light, which the light rays can then reflect off of a mirror. Or even if you had something that was simply illuminated. They see on the top of the next page a chess piece. You see it's a little bishop chess piece at the top of page 284. Top of page 284. Get those with me. All right. Well, let's suppose the light is shining upon a chess piece. The light rays that reflect off of this chess piece will hit the mirror. Now notice they account for the top of the chess piece and the bottom of the chess piece. Do you realize there will be an infinite number of rays coming off of the chess piece? But they only count for top and bottom. All the other rays are going to be somewhere in between anyway, right? So they track two parallel rays, the blue rays. They both hit the mirror, they both go through the focus, and that results in where the top and bottom of the chess piece would be. They also have two dark side of the force, pinkish-reddish rays that go through the focus, bounce off, and they reflect parallel. And where the two bottom rays converge from B, they would converge at S. The two rays from A converge at R. And it shows you how the image would be oriented. Again, you will not see a bishop, a little chess piece, unless somehow you had 3x5 card, 4x6, or some kind of card that you could hold up and kind of place, and you start to see fuzzy bishop, fuzzy bishop. As you brought it in right at that location, you'd see and tilted it just right, you get a nice clear image of a bishop reflecting off the mirror. You wouldn't see a bishop behind the mirror. You'd see that, or if you managed to put your eyes in just the right spot, it would converge on your own retina instead of on a 3x5 card. Okay, but you could get these images. Now, these images we've just pointed out actually reflect off a mirror and actually converge or are formed on the same side of a mirror. These are called real images. We're going to talk about that later. You don't have to write it down now, but that's a real image. A virtual image you can clearly see because it seems to be behind a mirror. The real images are more complicated because light is really reflecting off the mirror, and it's still on the same side of the mirror. So kind of a little unusual, but we see how these ray diagrams work. You need to know the three principal rays. The three principal rays. Now again, could you draw more rays than these in your ray diagrams? Absolutely. We're going to stick to three principal rays. The easiest of all of them is called the central ray. The central ray. The central ray is drawn through the center of curvature to the mirror and right back through. Through the center of curvature to the mirror and right back through. Why? Because it travels along a radius of curvature which is perpendicular to a tangent. Therefore, it's traveling along the normal with a 0 degree incidence. Therefore, 0 degree reflection. So it reflects along itself. The central ray travels through the center of curvature to the mirror and back through. If you wanted to look at, they don't have very many pictures like this. The only one they use the central ray on in these little pictures is, if you look at page 285, case 5. You see that green central ray drawn there. You saw it on the earlier page, though, that central ray going through the center of curvature, hitting the mirror, and bouncing right back along itself. These little arrows to show the directions. You see it travels in and then travels back along itself. Central ray, really easy to draw. It's just one line because it retraces. The next ray is the parallel ray. This kind of describes what we showed earlier, where it'll travel parallel to the principal axis and reflect through the focal point. Travels parallel to the principal axis and reflects through the focal point. When we draw our ray diagrams, we'll draw a ray that is parallel to the principal axis and reflects through the focal point. Now, you say, Mr. Dasky, how am I going to make a perfect parallel? You give it your best shot, okay? Fortunately, life and death is not determined by the accuracy of our ray diagrams. But you understand correctly, a parallel ray is going to be a little hard to make perfect, but we can go do a close approximation, all right? Computer generated is much easier, let's be honest. All right, the last ray is basically the opposite of the parallel ray. Instead of starting parallel to the principal axis and reflecting through the focal point, the focal ray can be drawn through the focal point and reflecting parallel to the principal axis. It's basically the reverse. So the focal ray can be drawn through the focal point, reflecting parallel to the principal axis. Through the focal point, reflecting parallel to the principal axis. And with the time we have remaining, we're going to do a couple of ray diagrams together. Turn, if you would, to page 291. Page 291. Let's start with a basic math problem. Problem number 4. Read that for us if you would, Audrey.
What is the focal length of a concave mirror with a radius of 12.2 centimeters?
All right, remember we said how do we find the focal length, class?
1/2 r.
Half the radius of curvature. So it gave us the radius of curvature is 12.2 centimeters, class. What would the focal length be? 6.1 centimeters, right? Half the radius of curvature. Pretty straightforward. All right, that's going to be important with the next problem. Number 5, read through part B for us, Michael.
An object 3 centimeters high rests on the principal axis at a distance of 15 centimeters from the concave mirror with a radius of 12 centimeters. Make a scale drawing and graphically determine the position and size of the image.
All right, so if you would, I asked you to bring a ruler with you and your compass with you. Students watching, if you do not have a compass and straight edge, pause the video and go get that if you would, please. Ideally, a ruler with markings on it. I don't know if Ms. Morse has one or not. In here, we can pilfer. Borrow. So, Kendall, do you have any markings on that there? Do you have centimeters by any chance? You do. Excellent. Okay. Good. I was wondering about yours. The others looked good there. If you would, go ahead and draw a line on your paper. A nice long line is good. And we're going to say that this line is our principal axis. We're going to go ahead and say that this line that we draw is our principal axis. Now, somewhere along the line, and not too far in, maybe come in, an inch and a half or so, we're going to mark a dot, and this is going to be the center of curvature. It's going to be our center of curvature. You'll need some space for this, Kendall. I don't know that you have enough room where you're at right now in your notes. You might want to do this on the next page. All right, then it says that the radius of curvature for number 5 was, class, 12 centimeters. So you're going to need to measure off 12 centimeters. Now I think I'll try to triple everything here. So I'm going to go 36 centimeters, but you do 12 and just make a little mark. So measure off along that line your 12 centimeters, make a little mark. And then if you would, go ahead and open your compass that amount. Now again, technically we should be in 3 dimensions. We can only work in 2. But make an arc. This represents the spherical mirror's surface. This point then being the vertex. Try best you can to draw equal portions above and below, if you could. And we also need to locate this focal point, because in order to draw either the parallel or focal ray, we need the focal point. Well, if the radius was 12 centimeters, class, what's the focal length? 6 centimeters. So measure back 6. Again, I'm going to triple everything, so I'm going to go 18. But go and find your focal point and label it F. So we have our center of curvature, our focal point, and our vertex. Now we are assuming that we're aiming the mirror directly at the object because it says that the object rests on the principal axis, meaning the mirror is aimed directly at the person or object in question. What kind of object will we draw? I don't know. I'm actually just going to draw an arrow so I can see the location, but it says it's 15 centimeters from the mirror. So if it's 15 centimeters from the mirror, that should put it 3 centimeters behind the center of curvature. So this is where my object's going to be, and it says it's a 3 centimeter tall object. So I'm going to draw a 3. I'm going to draw it triple again. I'm going to draw it 9, so everything's to scale. We've got our 3 centimeter object, 15 centimeters from the mirror, or 3 centimeters behind the center of curvature. And we want to determine where will the image be formed? How big will it be? Where will it end up? Well, the first ray I said we could draw, class, is the central ray. So with your straight edge, remember the central ray is going to be drawn through the center of curvature to the mirror. Now, we're going to start at the top of the object because we want to determine where the top of the object will form. So starting at the top, draw your central ray down through the center, hitting the mirror, and it'll go right back along itself. And I'm too lazy to redraw it. But it's going to go down this way and then reflect back that way. and there's my central ray. It just barely hit my mirror. Now, if yours missed the mirror, we'll ignore the central ray. There's three principal rays. I technically only have to have 2 of them. So if your mirror surface was too small to hit, so be it. All right, now, to be fair, Kendall, your object is not 3 centimeters tall. So it's going to turn out a little bit differently. And you're like, because I was noticing yours doesn't look the same as mine. And that's because your object was about 1 centimeter. So we'd want to draw it 3 centimeters. Well, that's a big object. Yeah, you're going to have a hard time hitting at that size. Something else isn't right. It's not. Yeah, yours is not quite drawn to scale here. Yeah, something's not right. You can still draw the diagram with us. It's just not going to turn out with the numbers the same way ours is. All right, the parallel rays is a fun one because we've got to try to approximate a line that would be parallel. And so from the top of the object, we'll draw a line parallel so that it hits the mirror. And then this ray, after it hits the mirror, will reflect where, class? Through the focal point. I'm not sure my parallel turned out too good, but whatever. So there's our focal ray. Or parallel ray, excuse me. Our final ray is the focal ray, class. That's going to start by going through the... It's called the focal ray. It's going to start by going through the focal point. Yes. And so we'll draw a ray that goes through the focal point. It's going to hit the mirror, and once it hits the mirror, it's going to reflect how? Through the focal point, and it's going to reflect parallel to the principal axis. So we'll try to approximate a parallel here. Now, is my drawing perfect? No. But we get the idea. Approximately right around here somewhere is where the top of the arrow should be. Somewhere in here should be the top of the reflected image. What about the bottom? Well, think about it. The central ray would go where? Stay with me. Central ray would go right along here and right back through, wouldn't it? The parallel ray would run right along here and go back through the focal point. The focal ray would go through the focal point and reflect back parallel. Since the bottom of the object is resting along the principal axis, the bottom of the object is going to be here. So, that's what my object would look like in the reflection. Notice, it'll be upside down. It'll be a little bit smaller than what I started with. In fact, if I were to measure it, I'm getting about 6.5 centimeters. Which if I'm dividing by 3 would be like 2 1/6. Maybe it's supposed to be almost exactly 2 centimeters, would be my guess. And notice it's not as far out. It's a little closer to the mirror, isn't it, than the object was. The object started at 15 centimeters. This one's only about 10 centimeters away. So we see that the object forms closer and also appears to be upside down, unlike plane mirror images. Right? We're going to be looking at this more in our next lesson about, depending on where you place the object, how is the image going to be formed? And we'll look at several cases of that in our next lesson. Now, homework this evening. Have a wonderful rest of your day, and you are dismissed.